the idea is that we're trying to optimize a function, and we have access to the derivative of the function, or the slope of the mountain we're going up. So if we know the derivative, then we can just walk up the steepest way to get to the top of the mountain in the quickest way. So this is what neural networks do. They take the derivative of the function we're optimizing and then run gradient descent. If we have access to two derivatives, this would be a second order optimization method, like Newton's method. And this is even more query efficient, although the computations between the queries tend to be a lot higher, so it's typically not used for deep learning too often. And then if we take one step backwards, if we don't have access to any derivatives, like if we're trying to optimize some discrete parameters, then this is called zeroth order optimization. And this is typically the setting for HPO and NAS. Okay, so next I'll talk about a couple baseline algorithms for zeroth order optimization. So say we're trying to optimize this function here defined by two parameters. And so the idea is that we don't know the value of the function anywhere, and we can start to query points. And when we query the point, we get the value. So this, you can think of this as like, say the x-axis is one hyperparameter, the y-axis is another hyperparameter, and then the function is the accuracy of the neural network. Okay, so the simplest thing is say we have a budget of 9 queries, then we can pick 3 for the x-axis hyperparameter, 3 for the y-axis, and then try all of these combinations in a grid. And the second, another easy algorithm is random search, where it's similar, but every time we make a new query, we pick both of them at random. And actually, random search typically does better than grid search. The reason is because in deep learning, it's very standard that some of your parameters will matter a lot, will be very important, and other parameters will not really matter too much. And in this setting, random search does a lot better because we get 9 choices of the important parameter rather than just 3 for grid search. And then the third type of algorithm is adaptive selection. So this is where first we pick a couple points at random, and then we adaptively select the next points based on the outcome of the first few points. Okay, and this includes Bayesian optimization, which I'll talk about a bit later in the talk. Okay, so another type of technique is called multi-fidelity optimization. So this is when, say we have a bunch of hyperparameters to try, and so the idea is that we launch all of them at once. So we launch like 100 different sets of hyperparameters, and then after 10 epochs of training, we realize that 50 of them just aren't doing that great. So we just cut them off right away. And then the better 50, we let them keep running to 20 epochs. And after that, we see 25 of them are not doing so great, so we cut them off. And then we keep doing this over and over until we let the best set of hyperparameters run all the way to the end. So this is called multi-fidelity optimization, because we're not just training all of the sets of hyperparameters at the same time, but we're trying multiple fidelities. Okay, so these are just, oh, and this is called the hyperband algorithm. And there are further improvements of this algorithm combining adaptive search called BOHB. Okay, so these are just a couple algorithms for hyperparameter optimization. And for the rest of the talk, I'll focus on some popular algorithms for neural architecture search. Okay, so in any good NAS algorithm, we want to consider 3 things. We want to consider the search space. This is we define the set of all architectures that we're searching over. And we define the search strategy. This is the algorithm we use to search over all the architectures. And then the third thing is the evaluation method. So this is like the previous slide. Do we train all the architectures fully, or do we train some of them partially? Or do we do something more complicated like train with shared weights? Okay, so I'll start by talking about the search space. So there are a few different types of techniques to define a search space. The first paradigm is macro versus micro search. So say we have a brand new data set that we know very little information about. Then we want, so we don't even know whether like a convolutional network or a recurrent network would do well. Then we want to do macro search, where we really want to build up a neural network from scratch with no human bias at the start. And on the other hand, another use case is we have some data set where we know a good amount of information. Like maybe we know that it's a image data set, so convolutions will probably work well. Then we would do micro search and search over convolutional networks to try to eke out the last 1 or 2% improvement. Okay, another type of search is progressive search. And this is where we start by searching over a pretty small neural network. Once we have optimized that pretty well, then we grow it a bit bigger, optimize over that, and keep progressively growing the neural network, searching bigger and bigger. And this is helpful because it's really hard to search over a huge network at the very beginning. So searching progressively tends to work a lot better. And then the final technique is cell-based search spaces. This has been very popular recently. And this is, if you look on the right here, we call this a cell of a neural network, which is about 10 nodes in a graph structure. And each node has some operation, like convolutional 3x3 or max pooling. And so we search over the cell, but then to get the full power of a neural network, we stack the cell on top of itself multiple times. And so this is a really popular technique because the search is over a smaller, easier setting, but we still get the full power of a big neural network. Okay, so next I'll get into the different types of NAS algorithms we can use. And I'll start by talking about Bayesian optimization. And this is a very popular method, especially for hyperparameter optimization, because Bayesian optimization is a great method to optimize expensive functions, or functions that take a long time to evaluate. And this is exactly the setting of deep learning because deep learning algorithms take a long time to train. Okay, so I'll just start by the inputs we need to start any NAS algorithm. So first we need to fix a data set like CFAR10 or MNIST. And next we need to fix the search space. Like say we choose a cell-based search space, like in the previous slide. And then third, we need to define an objective function. So typically this would be like the validation accuracy of the architecture after training for 50 epochs or something. Another popular choice is some combination of the validation accuracy and the number of parameters of the model. So this would bias the search towards finding more efficient neural networks. Okay, so these three things we need for any NAS algorithm. And then the fourth bullet point is specific to Bayes-opt. And this is, we want to define a distance function between architectures. And we want this to be quick to evaluate, and also have the property that if the distance is small, then the objective functions are fairly close together. Okay, and then the goal of neural architecture search is to find the architecture which maximizes our objective function, or at least get a pretty high objective function in the amount of time we have. Okay, so the framework of Bayes-opt is that we start by choosing a few architectures at random and evaluating them. And then we start this iterative procedure where we use the previous results to choose the next architecture to try, and then we evaluate that one. And really the heart of Bayes-opt is in the second to last bullet point, where how do we use the previous results to choose the next one to try? Okay, so the way Bayes-opt does this is first we need to assume that there's at least a little bit of structure in our search space f of a. And that's because if if this function was truly just random, then we would have no hope to optimize it. So we at least want to assume that it's a little bit smooth, like the pictures on the left here. Specifically, we assume that f of a looks like a Gaussian process. And basically what that means is that it's a smooth function and the deviations behave like Gaussian noise. Okay, and remember I said this was an iterative process. So the idea is that, say we've queried these 5 points so far, then since we assumed that it's a Gaussian process, we can start to compute error regions for all different values of our objective function. So like in this area, we have a pretty good idea of what the function would be, but in this area, we have a much less information about the function. Okay, so now how do we actually pick the next architecture? So we can do this by using an acquisition function. For instance, one of the most popular ones is called expected improvement. And the idea is that say we have this scenario here where we've queried 3 architectures, then over here we have a pretty good idea that the architectures here will be pretty good, but over here we know much less about this area of the function. So there's a 50% chance that the accuracy will be above this line. And in particular, there's a pretty high chance that it'll be much better than anything we've seen before. So the expected improvement for this point is very high. And so this acquisition function will tell us to query this point next. Okay, so that's an overview of Bayesian optimization. And next, I'll talk about bananas, which is an algorithm that we've invented here at realityengines.ai. Bananas stands for Bayesian optimization with neural architectures for neural architecture search. And the idea here is that Bayesian optimization works pretty well. But if you remember from a few slides ago, we need to define this distance function here. And it's a bit non-obvious how to define a distance function between two neural networks. So even if we have 2 feed-forward neural networks, it's a bit unclear. Like one of them could be like we could try something like edit distance, but then one of them might be offset by 1 or 2 layers. So it's a little hard to say what to do. And even worse, if we use a cell-based search space, then we just have 2 graphs, labeled graphs that we need to compare. So this is possible. Prior work has done this, but it tends to be a bit hand-wavy and maybe not a perfect distance function. So the idea for bananas is, what if we just throw out this Gaussian process altogether, and then we don't need to define a distance function at all, and we replace that with a neural network? So it turns out that this can potentially work much better. So the idea here is that in every iteration of Bayesian optimization, we have the subroutine where we have this neural predictor here that takes in architectures and tries to predict their accuracy. So in every iteration, we take all the architectures that we've already evaluated, train the neural network using these architectures, and then feed it in new architectures that we haven't seen yet, and then predict their accuracy. And we can even get uncertainty estimates too, if we have an ensemble of these neural networks. So then once we have accuracy and uncertainty estimates for all of these architectures, then we can just run an acquisition function, like in the last slide. Okay, so that's the general idea of bananas. And then one key step for bananas is how do we encode the architectures that go into the neural network? So it turns out that prior work usually sets up an adjacency matrix for the graph that the neural architecture represents, and then feeds that into the neural network. So it's actually an adjacency matrix plus a list of operations, because these nodes are labeled with their operation. And it turns out that this is sort of a a challenging data structure for the neural network to interpret. So the new idea for bananas is, what if we have a more path-based encoding? Because if we think about what this neural network is, it represents the flow of data from input to the output. So the data will come to the input, then go through these convolutions and the max pooling. And the idea is to just have every path represent a feature for our encoding. So what we do is we look at our search space and enumerate all possible paths that the data can take from the input to the output. And we make each of these paths a feature. And then for every new neural architecture that we want to encode, we look at all its paths. So these are all the paths of the neural network that's right here, like input, 1 by 1, convolution, 3 by 3 convolution, max pooling, output. And then we look at the feature that corresponds to that path and set it to 1. Okay. And it turns out that this encoding does much better than the adjacency matrix encoding. We saw that the error can drop by a factor of 4, actually. So we see this huge improvement. And then, so on the right, I have a plot of the final performance of bananas compared to some other popular algorithms. Okay. Okay, so that's all for Bayesian optimization-based approaches. Now I'll talk about a very different approach for NAS. This is a popular paper that came out 2 years ago called DARTS, Differentiable Architecture Search. And the idea for this approach is that, if you remember near the start of the talk, I claimed that NAS is a zeroth order optimization problem. But in this work, they found a way to cast it as a first order optimization problem, which allowed them to use gradient descent. So the idea here is that if you look at panel A, at the very start, we have no idea what operations should go on each edge. Like, we don't know whether this edge should be a ReLU or a 1 by 1 convolution or a max pooling. And so the idea for DARTS is, let's just try all 3 of them. So what we do is we put all 3 possible operations for each edge. And then once we do that, we add a parameter alpha for each operation. And so basically this acts as a weight, which is how much we weight each operation. And so once we have these weights for the operations, this is now a continuous hyperparameter that we can optimize. So that's exactly what they do in DARTS. So basically, the algorithm optimizes the regular parameters of a neural network, the weights, along with the hyperparameters, the architecture itself, simultaneously. So we start out with this huge neural network where we have every possible operation in each slot. And then we alternate gradient descent, where every even step we optimize the parameters, and every odd step we optimize the hyperparameters. And it turns out that when we run this to convergence, it gets a pretty good architecture in the end. Okay, so this is the algorithm. The upsides of this approach is that it's just a one-shot method, which means for BayesOpt, we might have to query like 100 neural architectures, whereas in DARTS we only train 1 neural architecture, although it is much bigger than any individual one. So that's a benefit of DARTS. One downside is that it's sort of this really big optimization problem where we're trying to simultaneously optimize the architecture and the weights. So it can be a bit finicky, and it seems to only work, or it seems to work better for the smaller search settings. Okay. And I'll talk about one final approach to neural architecture search. And this is reinforcement learning. So the idea here is that let's use a neural network to do the entire search for us. So in bananas, we used a neural network as a subroutine, but in reinforcement learning, we're just using a neural network to control the entire search not even use Bayesian optimization on top of it. We have some controller neural network, which is a recurrent neural network. And then the idea is that the controller in every round, it spits out an architecture that it wants to test. And then we train this architecture. And then once it's trained, we feed back the accuracy to the controller, which then sees how it did and then updates its weights. So in every round, it gets better and better at being able to output architectures that get high accuracy. And this is all set up in the reinforcement learning framework. So in particular, the RNN can take an action, which is it chooses which architecture to output, and then it sees a reward for that action when it gets the accuracy of that neural network. Okay, so this is the general idea. And the upside is that this is potentially more powerful than other approaches because there's a neural network controlling the entire search. But the downside is that this also comes with a lot more complexity. So we need to train an entire neural network to do this search. And so this can often be a lot more query expensive because it'll take more and more. We'll need to train a lot more architectures before the RNN gets really good at predicting new neural architectures. And another possible downside is that reinforcement learning might be overkill because, like I said earlier, NAS is really an optimization problem, but RL is this sort of extra machinery where we have actions and a concept of a state and reward. So it's really more machinery than just optimization problem. Okay, but still there are many popular NAS algorithms that use reinforcement learning. Okay, so this is all I'm going to talk about. So to conclude, I talked about AutoML. I gave some baseline algorithms for HPO, and I talked about some more interesting algorithms like the successive halving one. And then I talked about 4 different NAS algorithms: Bayesian optimization, bananas, gradient descent, and reinforcement learning. Okay, cool. So now I can look and see if we have questions. I see one question is, when you roll out the graph, how large models did you try? So that's a good question for the path encoding. So yeah, one downside of the path encoding is that it can be exponential in the size of the graph. But actually in our paper, which is on arXiv, we show that we can actually truncate the path encoding so that it's size n squared. So it's the same size as the adjacency matrix encoding. So that's a good point. At first glance, we might think the path encoding is inefficient, but we actually give theoretical results to show that it is efficient. Okay, so I think since we have 2 more speakers planned, I will hand it over to Austin next. But you can keep asking me questions in the Q&A or in the webinar chat, and I'll try to answer all of them. Okay, so now I'll hand it off to Austin, who will talk about how we use NAS reality engines to solve any data set or use case you want. Okay.
All right. Well, thank you, Colin. As always, that was super informative and appreciate it. All right, so I'm going to go ahead and start sharing my screen and also post a link in the chat, as well as just show you the link here in my browser. So I'm going to navigate you to the Reality Engine's classification workbook. So you can use this link. It's a bit.ly link, so it's bit.ly/uppercase R, uppercase E, _, and then in lowercase classification. And this will bring you to the Reality Engine's classification workbook. And for those who aren't familiar with workbooks, essentially they are a dedicated spot resource from Google, provided for us to be able to run code in the cloud without having to download Python, get your machine set up, install anything. So you can just run everything directly inside of your browser. And yeah, so that should get us going pretty quick here. But basically what we're going to be doing today is we're going to be taking a look at two different workbooks. The first is going to be the classification workbook. And so we're going to take a wine quality data set where it has a bunch of wine compositions for white wine, and then accompanied by a professional score of the wine's quality. And we're going to train a model using reality engines to actually predict, based on a new wine composition, what the quality of the wine is. And then after that, we're going to go to a regression workbook where we're going to address a regression data set where we have a concrete strength predictor. So based on a composition of concrete, we're going to predict how strong the concrete is going to be without actually having to mix the concrete. So once everyone has navigated to this link, and again, I posted it in the webinar as well, so you can click on that. But we will go ahead and get started. So the first thing that we need to do inside of this workbook is to create a Reality Engines account. So we're going to go ahead and click on this sign up link inside of, or in the first box. The sign up link does contain a special token which allows you to create an account. Reality Engines is in a private beta right now, and so you're going to be part of the first group of people actually being able to access the Reality Engines platform. So once you click on that link, it will bring you to the sign up page. And so all you need to do is fill in your name, email, and a password. So I'm going to head and start filling in that now for myself. So I'm going to give my name. I'll provide my email, as well as a password, in this case generated by Safari. Thank you, Safari. I'm going to go ahead and click sign up. And again, this is just the link inside of the sign up, or inside of the first box of the workbook. There's a sign up link. If you are still having issue at any point in this workbook, please reach out via chat or the Q&A. We have people on hand who can help out and make sure that you're caught up. We want to make sure that everyone in this workshop is able to train two models by the end of this workshop. So we want to make sure that everyone is able to follow along. And so let me know if you need me to slow down or you need me to address any questions. And so after you've created your account, the first thing that you need to do is create an organization. And so an organization in Reality Engines is a container which allows you to invite team members and create projects to solve different problems. And so we're going to just create a new organization. You can name this whatever you'd like. I'm going to name it Austin Corp, and I'm going to create my new organization. All right, and now that you've created your organization, you're now on the Reality Engines dashboard with your early access beta account. And the first thing that we're going to do, you can ignore the verify email for now. The only time that you need to verify your email is when you want to start inviting your teammates to join you on your project. But you should receive an email in a moment that will give you a code to type in to verify your account. But the first thing that we're going to do is create a API key. As we're going to use the Reality Engines API to train the model end to end. So we're going to click, there's a link in the bottom of the dashboard that says create an API key. Otherwise, you can click on your profile and then click on API keys on the left-hand navigation side. And go ahead and give your API key a tag. This is just so you know where you've used this API key. In this case, I'm going to call this my workshop API key. And now that I've created my API key, I can go ahead and copy it by clicking the copy button or by highlighting it and Command-C. And that And then once you have your API key, we're going to go ahead and navigate back to the workbook. And again, if you lost your API key or needed to navigate back, we provided links here in the workbook that bring you directly back to the API key dashboard, where you can create a new key or get the old key. All right, so now that we have our API key, we can go ahead and get started with the workbook. The first thing that we're going to do is install the Reality Engine's Python library. And so in order to run code inside of a workbook, all we have to do is hit play on each of these boxes. The first time you hit play, you're going to be prompted saying that Austin at Reality Engines authored this book. So we're just going to hit run anyway, and that'll start running the code. And once you have connected to your cloud machine, it's going to start installing the Python client. And secondly, we're going to import some standard libraries from Python. The first one is pandas. That's just going to allow us to preview the CSV file that we're going to upload to Reality Engines, and as well as pretty print, and that'll allow us to just visualize some of the outputs in a little bit more user-friendly way. So I'm going to hit play on this next box, and that's going to import the two libraries. And now for the second step, we're going to add our Reality Engines.ai API key. So that was the API key from the dashboard from just a moment ago. And so you're just going to paste your API key directly in this box that requests your API key, and then you hit play. If you hit play beforehand, it's going to assign an empty string to your API key. So just make sure that you paste it first and then hit play. If you hit play accidentally at first, just go ahead and re-hit it, and that'll set the variable correctly. And now if you've set up everything correctly, all you need to do is hit play on this next box to import Reality Engines and then initialize your client. And if there's no output after you've hit play, then everything is good to go. You've connected and your API key is valid. All right, so the first step, once we've created an organization and set up our development environments, is to create a Reality Engines project. And so the project in Reality Engines defines it's a container that defines all of our data sets, our models, and essentially is trying to encapsulate the business problem we're trying to solve. And so Reality Engines has a lot of use cases in our library that allows us to specifically address use cases that you might be trying to solve. And so we actually will use specific hyperparameters, machine learning algorithms, and AutoML to specifically try to address that business problem with a higher accuracy than just like a generic platform. And so what we're going to do here is actually list all the use cases available inside of Reality Engines, and we can use that directly from the API client. While this is not a super easy way of reading all the capabilities of Reality Engines, I do encourage you to check out the realityengines.ai website, where we have much more visually friendly graphics explaining each of these different use cases. But since we are trying to address a regression type use case, what we're going to actually select here is the predicting use case. And so for our predictive modeling use case, we're just going to set our variable use case to predicting. So I'm going to hit play on this next box. And then we should be, what we're going to do is ask Reality Engines what data we need to provide in order to address this use case. And so by calling the describe use case requirements, we're going to see that that in order to solve this use case, we need to provide a data set that's a custom table. And all that we need to provide is a target variable. So it's going to be the variable that we want to predict. And we allow two data types, categorical and numerical. And so for a classification problem, if we want to set a categorical column to a target. And so that means that we're going to try to predict a specific category. And if our target column was numerical, we'd try to predict a numerical value. And so it could be anywhere in the range rather than very discrete end states. So now that we know the requirements, let's go ahead and create our first project. And so calling the client.create project with the name wine quality and our predicting use case, we're going to create the project. And so by hitting play on this next box, we're given a project ID, and we see the name and the use case as well. So now that we've created the project, the next thing that we need to do is add our data set to the project so we can start training a model. And so Reality Engines provides a lot of data connectors to import or read data directly from our platform, whether it's from AWS S3, Google Cloud Storage, as well as you can also upload data directly to our platform. And we'll store it for you and train models from that. So for this workshop, we're actually going to import it directly from S3. And so we're going to go ahead and preview the value inside or the wine quality data set. So using pandas, the standard Python library, we're actually going to read the CSV directly from S3. And we'll just take a look at what's inside of this. So we can see by reading the CSV that we've got almost 1,600 rows and 12 columns. So we have acidity, citric acid, sugar, chlorides, and a bunch of different qualities of our wine. And then the final column here is the wine quality. And so this is going to be the score of each of these wines. And so now that we have our data set, we're going to use the Python client to tell Reality Engines where the data lies. And so it lies inside of a public S3 bucket, inside of Reality Engine's example data sets. And we're going to import the red wine quality wine data set. And so by hitting play, this will create the data sets and attach it to our project with the dataset type custom table. And so that was the value that's provided to us as the use case requirement or the requirements for this type of project. And so now that we've created the data sets, Reality Engines will go ahead and start reading the data from that location, and it will start processing the data inside of it, featurizing it, and automatically detecting all the column types. And so if you hit play on the next box, you'll see that by calling the get schema call, providing the project ID as well as the dataset ID, you'll see the schema that has been detected. So for each column inside of the dataset, we have a different schema object, and you'll see that some of these are numeric, or all of these are numerical except for the quality, which is categorical. And so it's been detected, even though those were numbers, that there is only a few discrete numbers provided. And so we automatically detected that to be categorical. So the last thing we need to do is just tell Reality Engines what exactly inside of this data set are we trying to predict. So we could flip this on its head and try to predict a numerical value given the quality and a bunch of other values, but in this case, we're trying to predict the quality. So let's say we're wine, we just bought a winery in Napa Valley, and we want to test different wines without having to pay the connoisseur fee to actually score our wines. We can create this predictive model to automatically predict what the final score is going to be given the data. So let's go ahead and tell Reality Engines what we're trying to predict. So again, describing the use case requirements in our data set. All that we need to do is set the target value. And so what we're going to do is call the client.setColumnMapping. And so the column mapping is just the target. It's a special Reality Engines type that tells Reality Engines what we're trying to do with the data. And so given the project ID and the dataset ID, I'm going to give it the column that I want to predict on and the column mapping target. And so after I call this, it's going to, again, return me the schema, but this time it'll show that the column mapping for the quality is set to target. And so we should be good to go. So the next step is to actually start training a model. So just to make sure that we've set everything up correctly, we can call on the wine project object, we can call .validate, and that will just check with Reality Engines to make sure that we have all the required data sets, all we have enough data provided for the system to create a model. And if we had any issues with our data set, it would show up inside of the dataset errors object. But we did receive a valid equals true. So we are good to go to start training our model. So for each of our use cases, we have different training options available. And so depending on what we're trying to predict and the use case we're trying to solve, we'll actually have different options for training. In this case, for our classification model, all that we have are the test split, dropout rate, and batch size. If you did want to play around with these, and I definitely encourage you to check them out, especially if you've trained deep learning models before, you can mess around with these and see if you get a better score. But given that we're doing deep learning AutoML, we are going to pick the best possible options for you automatically. So we should. We can just provide an empty dictionary for the training config, and we'll automatically select the best values. So what we're going to do here is call on the one project, we'll call .train model, and we can provide an empty training config. If I did want to mess with the test split, I could provide the test split value and provide it, say, a value of 5, and that'll change my test splits to be 5% of my data. And so I'll have a bit of a smaller test set. And so we support options anywhere in the range of 5% all the way up to 20% of your data. So I'm going to go ahead and hit play here, and that will go ahead and start kicking off the training. And so now Reality Engines is going and taking the data and training a model off of it. And so this will typically, for a data set of this size, take about 45 minutes. And so rather than sitting here and waiting for it, you will receive an email as soon as the training is complete. But while we do wait, we can go ahead and try out a pre-trained model. So last night I had trained the same data set, and I had gotten the model and then deployed that model to make it available for predictions. And so I've provided in the next line a prediction API call, which provides a deployment token, which authenticates only the predictions inside of a project, as well as a deployment ID, and then my query. And so the query is just one row of data. And so it's different properties of the wine, but of course without the quality, because I'm trying to figure out what the quality will be for this wine. And so if I hit play in this next box, it will make a prediction off of my pre-trained model. You'll see that of the wine quality scores, which are in the range of 3 to 8, we have a prediction that it's with 46% confidence, it'll be a score of 6, and with a 7% confidence, it'll be a score of 7. If we played around with this, say if we added a bunch to the pH, and so is more basic of a wine, you'll see that the score does indeed drop down to almost 100% certainty that this is going to be a 5. And so we can keep playing around with this, but what we're going to do next here is that we're going to jump over to the UI as the wine model is going to wait for the evaluation. So I encourage you to if you're in the workbook, to jump back to my screen, and I'm going to show off a pre-trained model here. So I've provided a checkpoint inside of your workbook. So at any point while you're waiting, if you do want to come back and check on your model, and you refresh your screen, or your machine got disconnected from the cloud machine, all you have to do is provide your API key here. And this will go ahead and look in your organization, find the appropriate project, and get your model back, so you can keep going along with the next steps inside of this. So all that we're going to do next, so let me go ahead and grab, go back to the Reality Engine site. I apologize, I need to minimize the zoom bar here. So let me go ahead and
Hi, Austin.
Oh, yes.
Sorry to interrupt. Just I see there are some questions in the chat window and also Q&A. Maybe you want to pause a little bit just to see we can answer on time.
Yes, so we have some questions in the chat.
Yes, I believe there are a couple of questions on the chat, and I think Colin replied. Maybe you want to speak it because we have some folks on the YouTube. So
Oh, of course.
Okay.
So let's see. So some questions from the chats, just so everyone who is on the YouTube can hear it. One of the questions was, what level of deep learning knowledge is necessary to use the AutoML, and what types of applications work well, not well with the AutoML? And an answer, almost all applications can be improved with AutoML. If there's a new data set, AutoML will give a good idea of the best model, even on popular data sets. AutoML still helps to get the last 1 to 2% improvement. And so definitely encourage you to try any of your data sets using the notebook or the Reality Engine's client. And you don't need to know any deep learning in order to use our product. We make it a very user-friendly interface to create new projects and solve use cases without having to have any background. So as long as you can provide our data, your enterprise data set to our platform, we'll handle everything from featureization through training, and all you have to do is tell us what you're trying to predict. And so let's see, any more questions?
There is a questions, I think Colin typed it, but maybe you want to just answer it here. So how do you decide the weight parameters of the regulators term in the objective functions in Bayesian optimization? Isn't that a search problem by itself? I'm not sure you can read it. It's in the Q&A. If you open that window Q&A and in answered.
Hey,
I'm
can you hear me? If you want, I can jump in and because I answered that question.
Oh, you already answered?
Or I typed it out, but I can I can speak it.
Yeah, maybe if you just kind of like read it to the answer, just make sure everybody both is on YouTube, they can see it too.
Yeah, so the question we got was about the Bayesian optimization algorithm I talked about, and the question is that how do we decide the weight parameter of the regularizer term? And that's a good question because yeah, these hyperparameter optimization algorithms themselves need parameters. So this is a downside of Bayesian optimization because we'll try to pick a regularizer that'll work good for all data sets, but sometimes there will be some data sets where the parameter doesn't work so well. So we might have to do hyper parameter tuning. And that's why some of the other algorithms I talked about, like the multi-fidelity one that don't take any parameters can work better sometimes. Okay, so I can pass it back to Austin now.
Okay.
There are a couple of more.
Yeah, I see a question asking about API keys. So just to do a quick refresher, so we scroll back to the top of the workbook. We do provide the special link for you to sign up and create a Reality Engines account. And after you create your organization, all you have to do is click on this second link here, the API keys dashboard. This will take you directly to I'll show you directly to the API keys section of the website. And here you can create your API key. And if you plug that into the workbook, it will very quickly, or all you have to do is like click through and hit play on a few of the steps to catch up to where we are and start your model training. And let's see, any other questions here?
I think if you go to the bottom of the chat, there are two more questions.
Okay. Colin, perhaps you will be able to answer this question.
Sure. So one of the questions is, does our service provide automatic feature engineering options? And yeah, so that's one of the most powerful things about deep learning is we can basically think about deep learning models as automatically featureizing the data. And this is true for any use case. For instance, like the classification one, Austin's demonstrating here, in the first few layers of the neural network, it'll like automatically find the best features, which is why deep networks are so powerful. We also see that in some of the other use cases like anomaly detection, where we use autoencoders to automatically encode the data. I'm not sure about I'm not sure what ONX compliant is. We can try to get back to answer that question. Okay.
Okay.
So one more in the Q&A. I'm not sure this one answered or not, so we can
There was one more in the Q&A that I think was a duplicate.
Oh, it's duplicate.
Another question that I answered. Yeah. Oh yeah, automatic feature engineering. Yeah, that's the one I just answered. Oh, and there's another one that's also duplicate. So yeah, I think we covered all the questions in the.
Okay. Awesome. Great.
Yeah.
Thanks.
Excellent. Okay. And so while our models are training, I just want to show you, or jump over to the UI and show you the Reality Engines platform. So if you can also navigate over here as well. You can click on either the link inside of the workbook that brings you to Reality Engines AI. Otherwise, go back to realityengines.ai and then click on the dashboard on the main page. And then you can find your wine quality project, which you created using the API client. And so if we jump onto this project, you can see that you have your wine quality data set. We provide a UI wrapper for confirming the schema. So it's asking me what exactly are you trying to set as your target. And of course, I already set it to quality, and it's just confirming that. And so I can see all of my columns inside of my data sets, all the data types that were detected. And again, they're all numerical other than the quality, which is categorical. If I open the raw data tab, I can view the section of the data set that I've imported. And so this provides all of the values for each of the rows. And so I can see a little bit more in detail of each of my rows. And then also we have a data exploration tab, which summarizes the data set for me. And so I can see that we have a very high rate of hits on 5 and 6 for my quality, as well as see the distributions for sulfates and the fixed acidity, the alcohol content. And so I can see how the distribution lies for my data. And then finally, we have the models, as well as the model metrics and a predictions dashboard. And so on the predictions dashboard, once your model is actually trained and deployed, what we have here is essentially a dashboard which allows you to play around with the values and just see that, okay, for each of these rows, I can experiment with test data. So I can pick a row inside of my test data set. So that gives me an actual quality. And so I can see how the model's performing as compared to the actual value. And so when I hit predict, you'll see that the histogram predicted this with a 54% chance of being a 5 and 39% chance of it being a 6. And then if I changed any of these values, say again, the alcohol content, and made that a 15%, you can see the prediction changed a bit here. So it's higher percent chance of being 6, a little bit higher of being a 7, and also a little bit higher of being 8 than previously. And then of course, we also provide the predictions API. And so this is just automatically generating example prediction using the API client. And so this is actually the code that was pasted inside of the workbook to create that prediction. So inside of Reality Engines, we have API keys, which allow you to manage all of your projects in your organization, import new data sets, but the deployment token authenticates only the predictions. And so this makes it easier and safer to embed this inside of a public-facing application, website, mobile app. So let's say you're creating a wine application, and you could import a bunch of different wine qualities. You can get a professional prediction on the quality and embed this directly inside of the user application. So it's not, and so you can provide more value to your product using these predictions. And now, before I keep going with this, I do want to go ahead and start opening up metrics. And so we have a lot of metrics on the model. And so this is how you will score how your model performs against the data set. And so as I had mentioned earlier, we have a split between the training data set as well as the test values. And so the model metrics allow you to measure how your model performed against the test percentage of the data set. And for that, I'm going to pass the mic off to Amar, who's going to explain the metrics and how to better qualify each of your models.
Yeah, thanks, Austin. Let me go ahead and share my screen. If you can stop sharing your screen. Yeah, so you might look at this page and you see all these numbers. You might be familiar with some of these metrics like accuracy or precision and recall, or you might just look at this and be completely baffled, and you don't know what this means and whether it means that the model is doing well or if it managed to learn your data appropriately. So I'm going to go ahead and actually talk about each of these metrics and explain what they are. In case you're not familiar with them, and hopefully better equip you to understand what these metrics entail and how to interpret the performance of your model based on these metrics. So let me switch to my presentation. Yeah, so those are the metrics that you see on our product. We have accuracy, precision, recall, area under the ROC curve, and log loss. And those are general metrics. They're not only related to machine learning problems, but they're applicable to any sort of classification problem trained using any kind of model. So they're quite useful and general metrics. Why have metrics in the first place? They allow us to compare models. So if we train different kinds of models, whether they're machine learning models or any kind of model, the metrics are sort of an objective way of being able to compare these models. It allows you to optimize for your objective. Each of these metrics tell you a different sort of aspect of the story of what your model, of how your model has learned the data. And depending what you care about, and the specific objectives of your problem, you might care about some of these metrics more than others. So, so understanding those metrics will help you optimize better for your specific objective. And then all these different metrics give you like a sort of wide picture of how your model performs and helps you understand what its strengths and weaknesses are. So we're gonna go ahead and do actually a small exercise, and we're gonna see how simple it is to compute all these metrics and visualize them. And hopefully that'll help you, once you know how they're computed, that'll help you better understand what they mean and how you can use them to analyze your model. So let's suppose we have this problem where we have a bunch of images. Some images are of dogs and some images are of hot dogs. And we want to predict which images are of dogs, and we want to train a model that'll learn which images are for dogs and which images are for hot dogs. And so those are our data points. We have 20 data points in total. 10 of the pictures are dogs, 10 are hot dogs. And then on this side, we have the model, and then we have what the model predicted for each of those cases. So picture where if our model predicts dog for a picture that's actually a dog, that's called a true positive. If it predicts a hot dog when the image is actually a dog, it's called a false positive. If we assume that the dog is our positive class. And then incorrect predictions for the negative class are called false negatives. Correct predictions for the negative class, in this case hot dog, are called true negatives. So the first metric that we have is accuracy. And accuracy is just the proportion of correct predictions that the model has made. So in this case, it predicted dog correctly, and all these points it predicted hot dog correctly. And so our accuracy is just the number of these points in these two quadrants divided by the total number of points. So we have 6 points in this quadrant, 8 points in this quadrant. That's 14 points divided by 20 total. That gives us 14 over 20, which is 70% accuracy. So it's the sum of the true positives plus the true negatives divided by the total number of points. And so accuracy might seem like a very general metric, and generally like higher accuracy is better, but it can also be misleading sometimes. And so here's a case where I'll go into that in a bit, but it relates to what is called support. And so support is pretty simple. It's just the number of points in the class. In this case, we have 10 points in each class. And so our support for dog is 10, and our support for hot dog is also 10. But so here's a case where it's important to understand what support is because it relates to accuracy. Suppose our model predicted dog all of the time. So it wasn't really a smart model. It would just, no matter what picture it got, it would just predict dog. And suppose this is the composition of our test data. Let me see. Yeah, sorry. And so in this case, we have 99 points that are dog and 1 point that's hot dog. That will give our model 99% accuracy, which might be a good thing, but it if what you care about is actually predicting the instance of a hot dog, then even though this model has really high accuracy, it's not really the objective that you're trying to achieve. So it's important to understand the limitations of accuracy, and calibrate the metrics based on what you really care about your model being able to do. So the next metric is precision, and precision is within a certain class, how many does your model predict correctly? So for each class, we can look at what the precision is, and it's just the true positives divided by the total number of points in the class. Sometimes for the negative class, precision is called negative precision, but it's the same thing. You look at the correct predictions divided by the total number of points in the class. So in our case, we have six correctly predicted points out of 10 pictures of a dog. So that gives us a precision of 60%. For hot dogs, we predicted 8 correctly out of 10. So that's a precision of, you guessed it, 80%. So very simple metrics. The fourth metric is recall. And recall is for a class, how many of the predictions are correct. So it might be a bit confusing, but you can think of precision as sort of looking at things, sort of looking at the rows, whereas for recall, you're looking at the columns. So you're saying for my model's predictions, what percentage are correct? And so for dog, among the times that the model predicted dog, it was correct 6 out of 8 times, which is 75%. Among the times that the model predicted hot dog, it got it right correctly 2/3 of the time, so 66%. So precision relates to sort of the actual distribution of points, so the dogs, and then how your model performs on that, and then recall relates to out of the times that you predict a certain class, what is your hit rate. And again, there's sort of the metric recall can go by several names. Sometimes it's called the sensitivity, the hit rate, or the true positive rate. And if you apply it to your negative class, sometimes it's called the specificity, selectivity, or true negative rate. So if you see any of those terms in the wild, know that they all refer to the same thing, which is recall. And so as you can see, the different those are all numbers to the same, apply to the same set of predictions and the same set of points, but they all give a different picture of and a more detailed picture of the model's predictions. And so if we go back to our example of this very skewed data set where most of our pictures are of dogs and we have a picture of a dog, the accuracy is really high and we get a precision of 1 when it comes to dogs, but actually we get a recall of 0. So in this case, the accuracy and precision, so in this case, adding the recall gives us a better understanding of the fact that our model is only predicting dog. And so there's this observed phenomenon of what's called a precision recall trade-off. And it tends to be the case that it's hard to maximize both precision and recall. Getting better precision usually comes at the expense of lower recall. But there's a point where you can get the best of both worlds and try to maximize both. And so that's what's called a trade-off. And you're trying to optimize the trade-off. There's a really important metric actually in classification, and this is the one that I actually would assign the most importance to usually when it sort of gives the most high-level picture of the model being of the model's performance, and it's called area under the ROC curve. It doesn't matter what ROC stands for. I'm not quite sure, but what's important to know is that area under ROC curve is a sort of measure of the model's ability to discriminate between the different classes. And ROC depends on the sort of notion of a prediction threshold. So usually in models, you don't just predict whether it's a dog or a hot dog, but you predict that with a certain probability. And so if we vary the threshold, we actually get different numbers. So we might predict everything up to that point as a hot dog, or up to that point. And that gives us different, and that gives us sort of different metrics. And ROC captures the notion of those metrics changing as you vary the precision threshold. And ROC is nice because an ROC that's closer to 1 means that the model was good, and AOC that's closer to 0 means that your model is not able to discriminate between the classes. So that's how you can interpret ROC. So those were the classification metrics. And I'm going to talk about regression metrics as well. And regression and classification are pretty similar problems. You can think of classification as sort of prediction over a discrete set, whereas regression is prediction on a continuous target or any numerical target. And so if you train a regression model on our product, you'll see these metrics. One is called mean absolute error. And mean absolute error looks at, so suppose those are our, those are our data points, and this line is our model's prediction. The error is sort of these red bars. It's the distance from our model's prediction to the correct point, or the correct data point. And so mean absolute error is just the average error over all the points. We sum up all the errors for each point, and then we divide by the total number of points. And then similarly, root mean squared error just looks at these are called residuals, these errors. So it looks at the sum of the residual square divided by n, and it's just another way of measuring the residuals. These two metrics are relative to the magnitude of your data. So there's, unlike AOC, where you just look at where it's just a value between 0 and 1, and then you know that 1 means it's really good and 0 means it's really bad. For MAE and RMSE, you have to understand the magnitudes involved in your data. So if we're predicting house prices that are on the order of hundreds of thousands of dollars. So say a house goes for $700,000 and our model predicts that it's $720,000. In that case, the error is 20,000. And so in that kind of scenario, if we get a mean absolute error of around, say, like 15,000, that's not bad at all. At least I think that sounds pretty good to me. Of course, it depends on your objective and what you think is sort of a reasonable amount. So there's always, even though these metrics give like an objective view of the model, there's always a subjective component that goes into it, and you have to like be able to know how those metrics relate to your objective. So yeah, MAE and RMSE are relative to the magnitudes involved. So they can be on anywhere from the order of tens of thousands, or a few decimal points depending on your data. Some other metrics include coefficient of determination, or R squared, and the mean absolute percentage error. These metrics are less relative to the data, and they're more sort of calibrated. Coefficient of determination gives you sort of the fit of your data, how well your model predictions fit the data. And like AOC, it's a value that goes from 1 to 0, where 1 means that your model has a perfect fit of the data, and it perfectly explains the variance and the potential outcomes. And fit of 0 means that your model has not learned the data at all, and its predictions are pretty much uncorrelated to the actual outcomes. Mean absolute percentage error is similar to mean absolute error, but in summing the residuals, it divides by the actual value of the point itself to sort of calibrate, to sort of get rid of the effect of the magnitude changing, based on your data. MAP has problems itself. Like sometimes, if your data has a lot of 0 points, then it's undefined. There's sometimes it's undefined, and there's like ways of getting around that, but it's also another good metric for sort of gauging what your residuals look like. So yeah, those are our metrics. I hope that it makes sense. I hope that it made sense. And yeah, feel free to ask questions on the chat. I'll still be hanging out. Let me pass this back to Austin now.
All right. Thank you, Amar. I'm going to go ahead and get back to sharing my screen in my workbook. So at this point, your model should have completed training. If you have not yet quite finished, you should have received an email if it did. If it hasn't quite yet, don't worry, we'll move on to the next workbook pretty quick here. But I did want to show you being able to get your model metrics through the API. So just to check to see if your model has completed training, this call on the wine model .wait for evaluation. Again, just in case you have closed your workbook, the link is bit.ly/re_classification. So give you a moment to jump back over to your workbook page and scroll down to the train a model section. So on the left-hand side, you'll see train a model, it's just above the checkpoint. And if you scroll down to the bottom of the train a model section, we have this block and call, which will essentially wait to see for your wait and keep checking continuously for whether or not your model has been trained. Once it has, it will return a value which with your model, and you'll have a status of complete. And so that means your model is trained, and we're ready to deploy it and start making predictions. If you did lose your session, you refresh the page, navigate it away, don't worry. All you have to do is grab your API key. And again, the link to the API key dashboard is at the top of this workbook. And if you paste your API key here, hitting play will reinstall the Reality Engine's clients. It will import everything that's required, and it will find your project. and grab your latest trained model. So if it is not done training, this box will continue to wait until it's done training. But once it is, it'll return your model object again, and you'll be able to complete this workbook. And so the last few steps here, we can, just like in the UI, see our model metrics directly through the API. So by calling this next step, we see all of the metrics that are talked about for the classification project. And so we have the scores for each of our class names, 3 through 8, as well as the micro average, macro average, and weighted average. We have the precision and the recall, as well as the support for each of these. And so this allows us to compare models. So if we try different training parameters, we could directly compare how our model performed, whether we're trying to balance for precision or recall or both. We can see to make sure that we're getting the scores that we are looking for. And again, we have a short form description of all of these values for you. So if you needed to come back and review, there are some descriptions directly here, as well as in our product as well in the help section. And so now that we have a trained model, we want to be able to actually use it and make predictions on it. And so in order to do that, what we need to do is called creating a deployment. And so a deployment essentially reserves cloud resources that host our model. And so this allows us to make really fast predictions on our model to get results immediately. And so what we're going to do is just on the wine model object, just call create deployment and then give it a name. And so what this will do in about somewhere between 4 to 5 seconds and 2 minutes, it'll spin up those cloud resources such that your model's ready and available. And so in your free trial with Reality Engines, your model will be deployed for free for 24 hours at a time. So it will automatically spin back down after 24 hours, but all you have to do is hit start on the dashboard and it'll start back up and you can continue to make predictions on your deployment. And then once your model is actually deployed, and again, this will take a minute or two. So there we go. My model is available. All I need to do is create that deployment token. And so as I had described earlier, creating a deployment token is a little bit different than our API key that we use. These deployment tokens only work on the deployments in this project. So this is very useful for being able to embed these prediction endpoints inside of your application without having to worry about the security as we use a different authentication system for the prediction APIs. And so now that I've created my deployment and have my deployment token, I can again make the same API call as I made earlier on my pre-trained deployment and get that prediction to see my predicted wine quality for these parameters. And so with that, we are running a little bit behind. So I'm going to go ahead and jump over to the regression workbook. If you haven't yet completed this workbook, I do encourage you to keep it open or to jump to the UI after the workshop, and you can continue to play around with the prediction tab. And we will go ahead and click on this link, which will bring us to the regression notebook. If you are joining late, don't worry, you can catch up. We are moving on to the second workbook. And so we won't wait as long on the creating the API key and such, but what we're going to do is navigate to bit.ly/R_E_regression. And again, as we're working through this, if you have any issues, have any questions, need me to slow down, please let me know in the chat, and I'll make sure to respond. Or one of my colleagues will be able to respond and help you out. And so once you're on this page, if you are behind and need to catch up, we provide a special link to the Reality Engines private beta. You can click on this link and create an account. And then you can catch up with us as we're navigating through this workbook, or go ahead and create your own projects after this webinar is over. And then once once you've done that, just navigate to the API key dashboard. If you left it in your other workbook, you can grab it from there. Otherwise, clicking on this will again bring me back to my API key dashboard. I'm going to go ahead and copy this and then go back to my workbook. And then just like last time, we're just going to install the Reality Engines client and then work through creating our project. So in this case, we are going to be tackling the other side of the predictive modeling coin. In this case, we're doing a regression data set. And so unlike the last one, the only thing that we're needing to provide is a bunch of columns describing our object, and then we just need to tell Reality Engines what we need to predict. And so in this case, the concrete, or we're going to try to predict the strength of a concrete based on the mixture and mixture of this content. So I do apologize for my dog. My wife will be taking care of that. There we go. So let's go ahead and get started. So we're going to click again on this first box. It may prompt you to run anyways, that you trust that Austin at realityengines.ai has authored this notebook. And so clicking on this first box will install the Reality Engines client. We're then going to, again, import pandas and pretty prints and provide our API key from the dashboard. Again, if you need that link, it's right here for opening up the API key, or the API key dashboard. You can copy it and paste it in here and hit run after you've pasted it into this box. And then once you have your API key, click play on this. That will import the Reality Engines API clients as well as instantiate it again. And we can go ahead and skip this list use cases as we've already seen that. But we're again setting it to predicting. So these use cases again are very similar. The only difference is our target value is going to be a numerical value rather than a categorical value. So there's no discrete set of possible values. It's going to predict a number given all of the inputs. So again, for the requirements for this, I do need to actually hit the use case above to set the use case to predicting. So make sure you hit this box to set use case equals predicting. And then when I rerun this, it'll show the values that I need. It's going to be the target. And again, the allowed data types are categorical and numerical. In this case, our target will be numerical. So finally, let's go ahead and create our project inside of our organization. So hitting play on this, we'll create the concrete strength project. And now we're going to go ahead and do the same thing as we had last time and preview our data. In this case, it is the concrete strength data set. So by hitting play on this next one, pandas will go ahead and fetch the concrete measurements from Reality Engines. So in this case, we have 1,030 rows. And so we have a bunch of columns here. We have the cement, slag, fly ash, water, and a bunch of other things that you can mix into concrete. And given these values, we have a measured CS-MPa. And so that's the measured strength of the concrete. And so we're going to train our model to be able to predict what the CS-MPa is going to be based on the other ingredients we're putting into our concrete. So with that, we can either continue along with this workbook, and I will jump back to this workbook in just a minute, but I do want to show you it's just as easy to do this from the Reality Engines UI. And so what I'm going to ask you to do, and again, you can feel free to continue with this workbook or follow along with me inside of the Reality Engines UI. What we're going to do is go ahead and copy this location. And so this is a S3 URI. So it's just a publicly hosted data sets inside of Amazon's blob storage. And so once I've copied that, I'm going to go ahead and jump back over to the Reality Engines UI. And so inside of the UI, if I refresh this, page, I should now see my concrete strength project. So if I open this up by clicking on concrete strength, it's going to, we have a tutorial built into the platform that shows you, okay, here's some stuff you can do. It provides you with the option to provide sample data sets. And so it'll automatically import a sample data set. So if this is your first time on the platform, we can walk you through how to, or an example problem. But in this case, we're not going to do that. What we're going to do is create the data set using this button here in the center of the screen. And now this is going to tell, or the box on the left will tell you, just like the list use case requirements, it's going to tell you all of the fields that are required for this data set. In this case, again, it's just the target value. And so that's required. And then also extra columns will be any relevant attributes. And so as we've seen from the pandas preview, we have a bunch of extra data that will help us, the model, predict the predicted strength. So what we're going to select here for, we're going to select upload new. And with that, we're going to give it a name. And so we're going to call this the concrete strength data. And again, it's the custom type or custom table type. And that's pre-selected for us. So after that, I'll hit continue. And now we can directly upload the file to Reality Engines. But what we're going to do today is import from the external service. And we're going to choose AWS for our service and then provide the URI that we copied from the workbook. And again, if you need that, that is in the workbook. Inside of the add the dataset to realityengines.ai. And it's in the location field in the create dataset call. And so it looks like it starts with S3 : / and then realityengines.example datasets. If this value is correct, when you hit add dataset, it will start inspecting. So it'll go and check that it can access the data, and then it'll start reading the data from the public bucket. And now we can go ahead and hit explore and train models while we wait for this data set to be inspected. It shouldn't take too long. But with that, as it's processing, we can go ahead and let's see. Shouldn't take more than just a second more, and then we can go ahead and set the schema. Just like in the next step, we do need to tell Reality Engines what we're trying to predict inside of our data set. Going to wait for this here. While we are waiting for that, if we see, I can go ahead and open up my other project and show you what this should look like. I do apologize. I'm not quite sure why it's taken as long as it is, but I'm sure I'll get through importing. I'm sure we have a bunch of data sets all being read at the same time. So while we wait for this, I will go ahead and jump over to my other project or organization, which already has this uploaded. So inside of this data set, and we have the concrete strength data, I can reopen that and open the schemas tab. So it will then prompt me to ask what target or value am I trying to predict. And again, as we had discussed, I'm trying to predict the strength of the concrete. So I'm going to select the CSMPA. And when I hit confirm and continue, you'll see that I have all the required columns that are needed. If I did want to ignore a column, let's say that I had a index or just the comments section, I could just add a tag it with ignore, and it will be ignored in our system for training. But we want to use everything inside of this. So we're going to leave everything as is. And so now that I've set my target, again, we can review the data. I see the raw data values, just like using pandas. And then also the data exploration, I can see the distribution again. So you can see it's a bit more smooth of a distribution for the values inside of this. data set. So we should see a bit more interesting results than the wine quality, which was definitely heavily weighted towards specific scores. And now that I have my data set set, we should see if I jump back over. Yes, okay. So now that my data set is done processing, I'll again go to the schemas tab. If you're on your dashboard, we'll actually see a step 2, which will ask you to set the schema. You'll see that the target is not yet set. So when I click on the confirm schema mapping, I'll select the CS-MPA. I'll hit continue. And now my schema is set. And the final step, as I'm being prompted by the UI, is to train the model. So I'll hit OK. And I'll hit train model, and just says through the API, we do have the advanced options available. If you want to mess with the values, we have options for the batch size. You can set the dropout rate and test split, and we'll also have descriptions and help for each of these. But I'll just give my model a name, or I can leave it as default, and it'll just be named the concrete strength model. So I'm going to hit train model here. And so this is just going to say that it's going to take a while. I'll just say, OK, sounds good. And now this has started training. So again, just like last time, you will receive an email as soon as your model is done training. While we are waiting for our models to train, I'll go ahead and jump back over to my pre-trained model. And we'll take a look at the metrics of the model. So we have the mean aggregate error, the score of 6.16, as well as the root mean squared error of a 7.9. And you can come to the help section to figure out what these mean. Amar had explained them in his talk when we had discussed the classification metrics. And then once we've deployed our model, we can make predictions on it. So if we go to the predictions dashboard after a model is deployed, we have a slightly different UI here. So instead of the classes that are possible, all that we see is the predicted value for this mixture. So given this value, this is part of our test data set. So we do have an actual value. So it came pretty close. If we provided, say, some changes to this, so let's say we wanted to add some more water to our mixture, predicting this, we have a predicted score of, or hardness strength of 38.78. And so we can, if we wanted to experiment and get the right strength for the job for concrete, rather than mixing a bunch of different concrete mixes, we could just test out different experimental mixtures directly with this model and actually be able to experiment much more rapidly without having to go through the work. And then all we have to do is confirm the actual values with our final, our best mixtures predicted. And again, we have the predictions API. So this is going to be the same value that you see inside of the workbook, where you can go ahead and, if you have the Reality Engines client installed anywhere, all you have to do is import and then make the prediction using your deployment token, deployment ID, and the example values. And you can run this directly in here and get the predicted value. So if you wanted to play around with your predictions again, you can change the values and then hit run, and it'll give you the actual values predicted on your model. And so this is a very quick way to embed your predictions as well. And of course, we provide other means of accessing. If you don't have the Python client, you can always make just standard REST requests, and we show you how to do that using the predictions API. So if we wanted to jump back over to our workbook, and I do apologize for the breakneck speed. We are running a bit low on time here, so I want to make sure that we covered everything and get everyone to their 2 trained models by the end of this workshop. And this workshop will be available on YouTube afterwards. So if you want to review what Colin's talk in the beginning on the science, as well as going through all these steps, it will be available via the link that is provided for the YouTube channel for AI Camp. But the last thing that we're going to do here is I'm going to show you how to resume your status inside of your workbook, as these models won't be done training before this workshop is over. So if you go to the left-hand side of your workbook and you click on the checkpoint link, you can provide your API key directly here. And assuming that your project name is the same concrete strength as I had written, this will just work as is. If you named it something different, just copy in the value of your project name. And what this API does is it goes through your projects inside of your organization. It will find your concrete project and it will wait for that model to finish training. And I provided an API key with a model that has already done training. So I do have that here. And again, we can just pick up from where we left off. And as we were waiting for our models to train, you can view the model metrics. It's the same values as in the UI. And then, of course, deploy your model. And so this will allow you to create your deployment and create the deployment token and then make predictions to predict how strong your concrete is going to be based on this input data. And I've provided links in both the top and the bottom of the workbook. If you just remember one, write one down, you can toggle back and forth between both the classification and the regression workbook. We do encourage you to continue to play around with the UI. As I had mentioned in the beginning of these workbooks, we have a lot of different use cases available, not just regression. We're using a lot of deep learning, and the science that was described just scratches the surface of everything this platform can accomplish. When you come to your project dashboard, do come to the create project in the top right. And this will show you all of the use cases available right now inside of Reality Engines. We're always adding more and continuing to improve all of these models in use cases. And so whether you're doing predictive modeling or recommendation systems, forecasting, or anomaly detection, we have all of these available for you to experiment with, upload your data to, and you can reuse your data sets in different projects, so you don't need to upload for each one. All of these projects allow you to attach already existing data sets from that you've already uploaded or attached to Reality Engines, and then you can quickly iterate and try different models. And so with that, I have about 10 minutes left if there are any questions that I can answer. Otherwise, I can hand it off to Bindu for some closing remarks. And I am, let's see, trying to figure out how to open up the question or Q&A section again. All right. And Bill, if you've seen any questions that have not been answered, I'm not seeing any at the moment.
Yeah, I see that 2 questions in the Q&A is even already answered.
Let me switch.
Yeah,
to
you open up with the Q&A.
Let's see, open questions. Post deployment, how do I call the prediction from a web app or mobile app? Okay, so I do believe I've answered that question, but after you've deployed, we do provide the REST API, which allows you to call it directly via whatever coding language or platform provides using a standard REST queries. Otherwise, we do provide that Python client, which doesn't require you to pass in an API key. You can just give it the deployment token and the deployment that you want to make predictions off of. And we will continue building out embeddable libraries to make predictions as easy as possible. But that should be, it's fairly standard in terms of being able to make those predictions. And what is the major difference in the code example between classification and regression examples? Actually, the predictions are exactly the same. It's using the same predict API and endpoint. So the only difference is the target value. And so based on what you're trying to predict, whether it's a numerical value or a categorical value, we're going to properly interpret and return the correct results based on what we've trained the model on. What is a good book for studying AutoML? I am not the person to ask for that. That would definitely be a Colin or a Mark question. I can defer to them, or they can answer via typing if they are still online. But I will definitely follow up at the very least with you and recommend some good books and reference on AutoML.
Hey,
and
I know there's a good survey on neural architecture search I like. It's called Neural Architecture Search, a survey. I think it's by Frank Hutter et al. Yeah, offhand I don't know a good one for AutoML in general, but I can try to look for a good one. Okay, cool.
There are two questions on the YouTube. Maybe I just read it to you. It's probably easier. Does the Reality Engine recognize the compressed dataset files like CSV.gz or zip files?
That is a great question. I do not know offhand. If we don't have that at the moment, then it will be in the pipeline very soon. But I do believe that we, yeah, I do believe that we work with compressed files, and we're constantly expanding the files that we recognize and take in.
Great. So that's going to be a feature request if we don't have one yet. So another one is from YouTube is, can I add my own metrics that do not exist? What about confusing metrics and other visualizations if I like to create them myself? How to do that?
Well, we don't currently support the ability to define your own metrics, but it did have test data. For example, you could generate your own metrics based off of the predictions for all of the test data. So we provide the ability to make those requests, and so you can create your prediction and see the output value, and then be able to compute your own metrics. So it shouldn't be very difficult at all to retest our models using the live or batch API predictions. And so you could have a standard test set that you could test against every model that you deploy. But we don't have any built-in way in the platform to do that.
Okay, so the last one, actually this part is more comments. You should add a progress estimation bar. The biggest problem with all machine learning platform is that you have no idea how long things will take. So it is relatively easy to solve problems, not trivial, but doable. So I'm not sure if I have any comments to, showing the progress bar when you're training the models.
Yeah, that's definitely a hard problem, as it depends drastically between problem types as well as the data that you're uploading. So the number of columns you have, the number of rows you have, all of those add complexities to the model. And we could also, we don't really know the end state until we get there. As Colin had mentioned in AutoML search, it is a search for the best hyperparameters and best solution. So we are getting closer and closer to a optimal solution as we get further along in training. And so there is definitely something to be said too, that once we have already trained a model once, we should be able to estimate how long it's going to take the next time, even if it's not 100% correct. So that's definitely something that we can start in terms of estimation. But it's definitely something that's hard to do when you're doing search in the way that we are for training.
Another one from YouTube. What are the limitations in the free account? I assume it's for the Reality Engine free account. What packages are available for individual students or hobbyists?
Okay, so the limits on your trial accounts is only that your deployments will spin down automatically after 24 hours. Other than that, you can upload any number of data sets, create any number of projects, train all you want, and just experiment. We'd be really excited if you reached out to us and showed us what you built. I think that when it comes to the free trial, yeah, we definitely encourage you just to use it as much as you want to really research and explore our platform.
All right, I think that's cover all of the questions on both Zoom and YouTube.
Okay, excellent. Bindu, do you want to close this out?
Hi. No, I mean, actually, I think, Austin, you covered most of it. And actually, Austin did mention to everyone who's on both YouTube and on Zoom, you can obviously go to realityengines.ai, request an invite, either for yourselves or for your organization. If you do request an invite for your organization, you can also invite your team members. We also have ML specialists who can do a free consultation with you if you have a specific use case. We strongly recommend, especially if you're really into kind of wanting to not just learn deep learning, but also wanting to put deep learning models into production, trying out various different predictive models using public data sets on Kaggle and elsewhere. It's fairly easy to do it. It'll give you a feel of what the machine learning workflow is, and also will give you a feel of how to like change various different parameters for either for training reasons or for like figuring out how the various different columns and the data works. So having said that, thank you for attending the workshop. Our next workshop, as Bill mentioned, is going to be on June 12th. There we'll focus on something which we haven't done before, real-time recommendations. So the idea there is the data will get ingested in real time using a streaming API, and it'll basically teach you how to create a real-time recommender system, which we think is a very powerful application of AI today in many enterprises. Thank you.